Hello everyone, welcome to my channel. So in this video I am going to discuss about maximal ideal of set of all continuous functions from closed interval 0 1 to r. This is a very important topic because from this topic in NBHM interview as well as in TIFR interview question was asked as well as in the written exam also. So that's why it's a very important topic. I believe this video will be helpful to all of you. Let's start. So observe, I define a set I see is set of all continuous functions from closed interval 0 1 to r such that f of c is 0. So my first claim is that IC is a maximal ideal. Question is why? So define a map f goes to f of c. You can see f is a ring homomorphism. And not f, this should be phi. Phi is a ring homomorphism and phi is onto. Then by first isomorphism theorem, kernel phi is isomorphic to R. Since R is a field, that will imply that kernel phi is maximal ideal, which will imply that this is maximal because kernel phi is precisely collection of all f such that f of c is 0. Right? So this is maximal. Now there is a very important question. The question: does there exist any maximal ideal which is not of this form, which is not of this form? I see. Okay, that means we can already see that we can just vary c here. Okay, I sub c, this is collection of all continuous function f on closed interval 0 1 such that f of c is 0. We can easily see that this is the maximal ideal. But now the question is, what about the all types of maximal ideal of this ring C01? Does there exist any other type of maximal ideal, or this is the only type of maximal ideal? The answer is that every maximal ideal is of this form, which is very interesting, right? So answer is that every maximal ideal is of the form this, right? Okay. So how to prove this? The proof is very interesting. Let I be a maximal ideal. Okay, assume that I is not of this form. Then for any a belongs to closed interval 0 1, there exists a f depending on a belongs to I such that f of this is non-zero, right? Because I am already assuming that I is not of this form. If such a if there exists a such that f of a is 0 for all f, that means that is of the form IA, right? I am already assuming that I is a maximal ideal which is not of this form. That means for any a, if I choose in closed interval 0 1, I can always find a continuous function f suffix a belongs to this ideal such that f a is non-zero. Okay, then by continuity there exists a neighborhood of a where f is non-zero, right? By continuity of f a we can find a neighborhood of a, say v f a, such that v for all x in v f a of x is non-zero. Then clearly a is inside this because this is the neighborhood of a. Then 0 1 0 1 closed interval 0 1 can be covered by this open set VFA, right? And we know 0 1 is compact. Then every open cover must have a finite subcover. Right? That means there exists A1, A2 up to AN belongs to 0 1 such that 0 1 is contained in union of I equal to 1 to n V f of ai. Right? That means in particular f of ai belongs to I. That means f of ai square belongs to I because I is an ideal, right? And I is a maximal ideal. I am already assuming. Okay, this is in I. Now then f equal to f a1 square, f a2 square, dot f an square, that is also in I. Okay, because f ai square in I, so that means their sum is also in I. Right? So f is in I. Now claim fx not equal to 0 for all x belongs to 0 1. Why? Why this is true? It is easy to check. See, let f of y is 0. That means y is 0. That will imply f of ai square y is 0 for all I n. But y belongs to vf of aj for some j, right? Why this is true? Because we know that 0 1 is already covered by union of this v of f of a, and y is an element in 0 1, right? That means there exists some j such that y belongs to v of f of f aj, right? v of f aj, and then by our assumption f aj of y must be non-zero because we are choosing the neighborhood in this way, right? We are choosing this neighborhood in this way, so that means this is non-zero. That's a contradiction, right? Hence f of y must be non-zero for all y belongs to 0 1. Then f is an unit. And we already assume that I is an ideal, right? We already assume that I is an ideal. Then f cannot be inside I, because if an unit inside an ideal, that means the whole ring inside that ideal. That means I cannot be proper, because a maximal ideal is a proper ideal. That means it will imply that I is exactly R, which is a contradiction. I mean, R means that ring here, which is C01, which is a contradiction, right? So observe that here we have already used the compactness of 01. You can generalize the same question, and this is also true in any general compact space. Let K be any compact subset of R. Okay, in particular any compact metric space also. Then CKR has maximal ideal of the form IC. Every maximal ideal is of this form. Okay. Now the question is, what about if that is not compact? Okay, so let's take open 01. This is also an interview question. Okay, so let's see open 01. So we can see that we can't use the same procedure for 01 because 01 is not compact. It's not compact, right? As it is not closed in R. So that means this is not compact. Now can we say that all the maximal ideal is of that form? That is not, because so consider an ideal I, okay, collection of all continuous functions such that f of 1 by n is 0 for all but finitely many n. Right? So you can see that this is an ideal. Why? Because if f of 1 by n is 0 for all but finitely many n, and g of 1 by n is 0 for all but finitely many n, so after a finite stage, for all n f of 1 by n is 0, as well as after a finite stage g of 1 by n is 0 for all n. Then you can take the maximum, and then after that finite value, f of 1 by n as well as g of 1 by n is also 0. That means f plus g is also belongs to I, and product is obviously belongs to I. It is easy to check, so that will imply that I is an ideal. I is an ideal. Then since 01 is a commutative ring with unity, that means every ideal is contained in some maximal ideal. This is a standard theorem. Some maximal ideal M. Right? So that means I is contained in M. Now the question is, M equal to I suffix gamma for some gamma belongs to 0, 1? That is not, because if M equal to I gamma, then f of gamma is 0 for all f in M. In particular, f of gamma is 0 for all f in I. But what is I? I is an ideal where we are defining that f of 1 by n is 0 for all but finitely many n, right? So choose k belongs to 0, 1 such that 1 by k is less than this, right? Then define f such that f of define f such that so define f such that fx equal to 0 for all x less equal to 1 by k, and then define in such a way such that f of gamma is non-zero. You can just particularly see, say you have just 0 1 here and say 1 by k is there, so define a continuous function in this way. Okay, so this and then this, you can define it. This is also 0, and from this part f is identically 0 on this, on say 0 comma 1 by k. Then clearly f of gamma is non-zero, and you can do it for any form, right? That means clearly the maximal ideal is not of this form. Hence there exists maximal ideal which is not of this form. That means the above claim which we have already did, that is true for compact space. In general it is not true. Okay, I hope this is clear. If you have any doubt, just comment below.